IB, Palma Mallorca, Spain. He's going to talk to tell us about the biased voter model. Raúl,
okay.
Please.
Okay, thank you. Of course, I would like to thank the organizers for the effort they have done into this meeting. It would have been nice to be there in Sao Paulo, but still I think the meeting is going quite well from the pure scientific and also from the technical point of view. So I hope you can hear well my presentation. Okay, this is about the biased voter model. And of course, I mean, there is no need. First, I would like to thank my collaborators in this work, which have been Max San Miguel, who also gave a talk here, and Agnieszka Czapliska and Christos Karamboulos, who are postdocs at IFISC at our institute. You know, there have been already many talks introducing those models of social behavior, so I don't really need to introduce why we're doing that and so on. But let me just tell you the model I'm considering is the voter model. The voter model is a model for imitation. And we, as people, we do things just by imitate. We buy a new iPhone because our neighbor has got a new iPhone, whatever. And this idea that we simply imitate the behavior of others has been called this herding behavior, has been actually used as a real mechanism to understand the dynamics of social groups of people. For example, this paper by Alan Kirman, who is an economist, used this imitation mechanism to understand how the stock market works. So it's similar to this cartoon. In his model, in the model of Alan Kirman, the brokers take a decision on where to sell or buy simply by imitating what others are doing in the market. From there, he can derive some interesting properties of the market, like the non-stylized facts and so on. I'm mentioning this because there are many interpretations to the voter model. I'm mentioning this just for personal reasons, because that's the way I reached that model. Okay, the first paper I saw on the voter model was the paper by Alan Kirman. So I'd like to explain it in this way. Now, as I said, the voter model uses a mechanism of imitation. Okay, perfect imitation. You can also have imperfect imitation. You can have that you imitate, but not with a perfect probability. That maybe has an origin in the noise and the free will. This is called the noisy voter model. I will not be considering the noisy voter model today. I will consider just the voter model. In the voter model, one thing is the mechanism, which is imitation, where I'll be more precise in a moment. And then the second ingredient is who interacts with whom, which is the network of interactions. And of course, the most popular networks are the all-to-all, in which everybody interacts with everybody else. That's also called mean field, although this mean field is a bit misleading, the words mean field here. And also the consideration of complex networks, in which you have some degree heterogeneity. So not everybody has the same number of neighbors. Of course, there is a question of coevolution, in which the links can vary, and also Maxi gave us a talk about coevolution, which is important. I will mention something about that at the end. Now, in this model, there is only one question, one important question we want to answer, and it's the following. Given this imitation procedure, is the ultimate outcome consensus? Consensus meaning a significant majority sharing the same opinion. Perfect consensus means everybody sharing the same opinion. Imperfect consensus means a significant majority, 80, 90% sharing the same opinion. So that's the question we want to answer within this model. And the question might seem trivial, but it is not trivial. And that's why I think the model is interesting and has attracted a lot of attention. There have been also other talks about the variance of the voter model in this conference. So why we as physicists, or me as physicist, I'm studying this? Because this transition between consensus and lack of consensus is reminiscent of this disorder, paramagnetic liquid gas transition in statistical physics. Of course, there is a main difference, is that here we have a non-equilibrium setup. We don't have a Hamiltonian, we don't have a detailed balance in the stochastic rules. So let me define the model that was already done by Max. I think we share the same slide. Is that we have voters which are located in the nodes of the network. The interpretation, I say, can be varied. It can be brokers selling or buying options, can be speakers using one language or another. There are many interpretations of this model. I will not enter into that. And the rule is very simple. A randomly chosen voter takes the opinion of one of its randomly chosen neighbors. That was the model that was introduced in the 70s. So we have two options, +1 or -1, red and blue or whatever. And then you select one neighbor, randomly, this neighbor selects another neighbor randomly, and the first one, which is red, will copy the blue, state blue. That will be the dynamics. Very simple dynamics. And then the simple dynamics, you realize that here we have two particular states, which are the absorbing states. The absorbing states are the perfect consensus. When everybody is blue, when everybody is red, dynamics stops. There can be no further dynamics. Okay, these are absorbing states. And then the question is whether consensus is reached. It's a question of whether one of two absorbing states is reached, and what is the effect of the networks of interactions in this result. If we are talking about consensus, we need a measure of consensus. So we'll give you two measures of consensus. One is simply the fraction of nodes in the state one, which is sigma. And also you can be, that's one measure of consensus. And then the second measure is called rho, which is the density of active links. This is the number of active links, which is an active link. An active link is one that links two agents in different states, +1 and -1, or -1 and +1. These are the ones that can evolve. That's what they call active links. Of course, when there's consensus, there are no more active links, so rho equals to 0, and the density can be either 0 or 1. That's why actually rho is preferred to sigma, because rho takes a single value in the consensus, whereas sigma can take two different values in the consensus, whether you have the consensus in one or the other. Well, then let's give the answer to this thing. Is consensus reached? Of course, this is stochastic dynamics. Consensus is one of the states. It's an absorbing state. The model is ergodic. There is no way you forbid one transition from one state to another. So eventually, you will always reach the absorbing state. Once you reach it, dynamics has stopped. So problem solved. Consensus is always reached in a finite system. So I could have stopped my talk here because this is a simple problem, and so, but no, it's not so simple. Let me tell you why this is not so simple. The bottom model, as I say, can be solved in regular lattices, and that has been done. And here we have to distinguish the results for a finite lattice, which n is finite, or the thermodynamic limit, which we physicists like to take, in which the number of particles takes to infinity. In a finite system, we always reach an absorbing state. Now, how long it takes to reach absorbing state? Well, in one dimension, I mean that's a ring, you take a time which scales as n squared. In two dimensions, it goes as n log n. When you take the infinite limit, this average value, the density of active links, decreases monotonically with time, as t to the -1/2 in one dimension, or 1/log t in two dimensions. Okay, that's how you would see a simulations. That's the result for the infinite system size. And you see that the system size increases, you see that it takes longer and longer for rho to decay. But all of them decay eventually for finite n. And it takes an infinite time to do it when n is infinity. But the surprise comes when you go to dimensions larger than 2. Dimensions larger than 2, including the all-to-all and including some complex networks which have an effective dimension larger than 2, what you see is that the density in the thermodynamic limit tends to a finite value. So it decreases like this. It decreases towards a finite value. In the infinite size limit, it remains there for a long time, for infinite time. But in a finite system, what it does is to move around this state until a finite size fluctuation takes you the system to the absorbing state. Okay, so the picture on the right is what happens when you do realization. Look at the log scale. What happens? You do realization of this model. So they stay for a relatively long time in this metastable state until eventually there is a finite fluctuation, a large fluctuation that takes you to the absorbing state of rho equals to 0. If you average, you get an exponential decay. That's an average over many realizations. But this tau increases with n, increases actually as n. So now we have to understand this n at not really the time to reach consensus, but also as the survival time of a metastable state. So the system stops for a while, oscillates around this well-defined value for a while, and then until finally goes to the absorbing state. Now, there have been many variants of the bottom model. Bottom model, as I mentioned, the noisy bottom model. There have been talks here about the nonlinear bottom model. By Alan yesterday, the Q bottom model, the aging, contrarians, zealots. I mean, there are many, many modifications of the bottom model. I want to focus here in a variety in which we have a preference for one of the two options. So far, I have considered two options, red and blue, were equivalent. I want to consider the case in which there is a preference for one or two options. This belongs to also there have been works in this direction. It's called the Partisan voter model, in which which agents have a preference. Every agent has a preference for one or the other option. That has been applied in physical systems, and in language models, you can have that one of the languages is preferred over the other language. Okay, so that's quite natural to study in this context. So what I want to consider here, more specifically, is the following setup. We have a fraction gamma of agents that have a bias towards the opinion +1. Would be the -1, but I choose +1. Okay, so it's a fraction of agents. We have a bias. So this fraction gamma is biased. The rest is unbiased. This is the setup I'm going to consider. Now, what are the rules? The rules, what do I mean by bias? So how do I do in practice the bias? So I pick an agent at random, and then I pick another neighbor. So the agent that I have picked in the first time could be unbiased or biased. If it is unbiased, it simply copies the state of the other with probability 1/2. Not 1. This is a minor modification. This simply introduces a factor of 2 in the time scale, but it's more convenient to use this 1/2 than to copy with probability 1. But the difference is that when the node that I have chosen is biased, then if that node was in the +1 opinion, which is the preferred one, it doesn't like to go to the -1. So it copies that with a probability less than 1/2. On the other hand, if the state was -1, but still it is biased towards 1, this is something that also was addressed by Katarzyna in the first talk, whether you have a different opinion of what you prefer. Then when you have an opinion -1, but you prefer to be in the +1, you copy this opinion +1 with a probability larger than 1/2. Again, very simple rules. Nu of this V is the bias parameter. And if you have nu equals to 1, it's an agent that never changes his preferred state. That's a 0, and that will be another chunk. Okay, so I will not consider 0. In fact, I will consider that V is a small parameter in most of my simulations. V will be small. And then I need interaction network, which can be a complex network. And here I'm explaining what I'm saying. A bias is red, so a bias copies a -1 with probability less than 1/2. A bias copies +1 with probability larger than 1/2. Okay, this is the model. So questions: is in this model consensus always reached? Is +1 always the favored consensus? How long does it take to reach consensus? How do results depend on the network structure? Then we consider three different setups. One is the mean field, the all-to-all interaction. Then some random topologies, Erdős-Renyi network, and then we'll see how we can organize the agents in order to obtain different results. And then we'll focus on two quantities. One is the probability to reach consensus in the preferred opinion, and the second is the time that it takes to reach this consensus. Okay, these are the two things I will focus to answer the previous questions. So some theory. Well, this is standard, okay, but let me just tell you how we do that. I will not give you many of the details. I'll tell you the starting point, okay, how we do this. We consider first the all-to-all interaction, so that we in this limit of all-to-all. In the limit of all-to-all interaction, that's nice because there is only one relevant variable, which is the fraction of nodes in state +1. The density of active links in this all-to-all actually follows the fraction of nodes through this exact relation. Okay, in the all-to-all, this is exact. So rho and sigma are completely equivalent, and this is usually approximated by 2 ρ1 minus rho when n is large. Okay, so there is only one variable that we need to consider. Then what happens to this variable sigma? Well, when you do one single spin, sorry about that, I'm using this word which I not introduce, but you know what it means. Update, this density can increase or decrease by 1/n. One agent will change from -1 to +1, so sigma will increase by 1/n, or it will go from +1 to -1, so sigma will decrease. And then this is a random walk in the space of sigma with those probabilities. Probability that sigma increases is called R, going to the right. Probability that sigma decreases is called L. How do I compute these two probabilities? So let me just tell you very quickly how to do that. So what's the probability that sigma increases? What do you need for sigma to increase? Well, you need to choose one agent in the -1, and this wants to copy an agent in the +1. How is the probability of this copying? Well, if I is not biased, it copies with probability 1/2. If I is biased, I copy with probability larger than 1/2. For this, I use base rules. Probability of SIB minus 1 times this conditional probability, and I put there what I have, and then I consider that this probability of S being in the state plus 1 is independent of minus 1. So this is equals to sigma. The probability of minus 1 is 1 minus sigma. And here you simply have this gamma, which is the fraction of biased and unbiased. And then we get this final result for this rate. Similarly, you get this for the probability of going to the left. A very simple question. Just to mention that the basic ingredients of what we're doing. Once you have this, everything is very simple. You can write a time evolution for the mean value of the density for the density of nodes in the one state, which is simply the R minus L. I think you can solve this, and then you can see that the density, the fraction of links in the one state decreases, increases or decreases exponentially towards plus 1 with a characteristic time 1 over gamma b. So problem solved. Consensus is always reached because you always reach sigma equals to plus 1 in a finite time, which is 1 over gamma b. Well, maybe not so quick. Not so quick, because we have neglected stochastic effects. That was a mean field treatment. And still, within the all-to-all, we can have stochastic effects. There are many ways of doing that. For instance, you could improve upon this evolution equation by including the stochastic effects, but let me analyze that in a different way, which is also standard. This is a standard way of analyzing these problems here. And I would like to mention how to compute. We use the standard machinery of random walks. So how to consider this probability of reaching the state plus 1? Well, starting from an initial fraction sigma, well, you do the following. In a time step, sigma will increase, decrease, or stay the same. So the probability that you reach 1 starting from sigma is the probability of moving, probability of moving to the right, and then you start from sigma plus delta sigma, or you move to the left, you start from sigma minus delta sigma, or you stay and then you keep from sigma. Okay, these are the recurrence relation, which I write here. These are the relation that you need to solve. The solution of this is what I plot here. The solution is what I plot here, which is so this is the solution of the probability of reaching the preferred state. It is more convenient to work with a continuous version of this, in which you expand in 1 over n. And take the limit n going to infinity, and we replace this by derivatives. So we get a partial differential equation that we need to solve with these boundary conditions, and this is the solution. Okay, so we have two different solutions, this one, and we can compare them. And actually, the continuous limit solution is an excellent solution, as the difference between both we can prove that is less than 1 over n squared. Okay, so let me show you the results. The results are not very exciting in the sense that all these for the all this theory works very well. So here I plot the probability of reaching the consensus in the plus 1 state, and you can see one thing: this probability is not 1. So you may reach consensus, but not necessarily in the preferred direction. Of course, if n is very large, if gamma of v is very large, I remember gamma is the fraction of bias agents. V is the bias, and n is the number of agents. If this is very large, you reach 1, but you might reach consensus on a different state. You can reach consensus on the minus 1. So you reach consensus, but not necessarily in the preferred direction. Okay. Now, how do you compute the time to reach consensus? Again, you write a recurrence relation for that. I don't want to enter to that because I'm running out of time. Simply, you can write a differential equation for that you could solve. I'm showing that here just to show you because we're very proud of this. Took us some time to find the solution. And then you can find the time to reach consensus to any state, which is tau, or the time to reach consensus in the preferred state. And instead of showing the formulas, I show you how they look like. So this is the time to reach consensus, tau, the time to reach consensus, as a function of the initial percentage of agents in the state plus 1. Of course, if you are in 0 or in 1, you are already in consensus. So tau is 0. Okay, that's different. And the time gets a maximum, which depends on the bias. I find amazing that the time to reach consensus in the preferred direction and the time to reach consensus in the in overall coincides for sigma 1/2, which means that for sigma 1/2, it takes on average the same time to reach the preferred or the non-preferred state. So you have a bias dynamics, but the average time to reach one or the other is the same. You reach one more often than the other, but the average time to reach is the same. You can also check how this time is scaled with n. So let me show you these results here because I want to get to the second part. I'm going to do it fast because you can take the results when this parameter beta is this combination. When n goes to infinity, beta goes to infinity, and you can check that this time scales at the logarithm of n instead of as n as it happens in the unbiased case. So with bias,
20 minutes. How?
Okay, yes, I have my clock. So with bias, you get a much faster approach to consensus. It's a logarithmic divergence with it. Now, let me go to the issue of complex networks. Okay, that was the old tool. So I want to consider complex networks. How do you do that? Well, this is more complicated. So I want to make, I would like to advertise two papers. Well, the first one doesn't need to advertising. It's a well-known paper by Gleason, in which he summarizes and introduces methods of doing these binary state models in complex networks. Maybe I want to focus this attention on this more recent paper by myself and Tony Peralta doing the stochastic. The only difference is the stochastic version of what Gleason introduced. Okay, in here, when you do complex networks, the key point is to introduce new variables. Now, the density of active links is no longer a variable that follows blindly this relation. This is an independent variable. So what you need to do is to include in your description two variables. And then you need to redo everything taking into account these two variables, that the number of active limbs is not any longer given this quantity. You can then modify your probabilities to copy, introducing the density of active links. Then you can do the pair approximation, which assume that this probability of an active link is independent of other links. You can compute the rates, including the two variables, including the sigma variable, and then you get, after some long algebra, you get these couple evolution equations for the density for the fraction of agents in the one state at the density of active links, and then you need to solve this in parallel. Okay. In the case nu equals to 0, in which there is no preference, you can determine the non-trivial steady state. And that was done. I want to mention this paper by Vázquez and Eguilos a time ago, where they compute this steady state, which coincides with the one you obtain as a metastable state in the simulations. Now, how do we do that here? Again, I will not give you many results. The thing is that you do some sort of adiabatic approximation in which rho follows the sigma variable. I'm sorry, I'm a little bit late, but what you can do is that you can follow within this approximation, you can find how rho varies with sigma. And you can see that here we have introduced the effect of the bias here. When the bias here, we recover the previous result. When the bias is present, we recover this new result that we have checked. This is how we check this formula, and we can see it works very well. And this formula has the necessary limit in which the bias is 0. It tends to the well-known formula for the unbiased case. And also when mu goes to infinity, when the connectivity goes to infinity, it goes to this exact relation, which has to be necessary in the O2O limit. So let me tell you how this goes. So what we found here is that the density of active links again finds a state in which it remains basically constant. But now this depends not on system size, but depends on this combination. So this state of almost constant lasts for a time which is 1 over gamma b. So we find that eventually you do reach consensus, but you spend a time which is inversely proportional to the bias in a state which is metastable. Right? Not metastable, which is a state that lasts a long time. At the end of the day, everything is a bit depressing because all this network effect can be summarized into a single parameter. So all the network effect can be summarized by varying the size of the network to an effective size, which is equal to the real size multiplied by the first moment squared divided by the second moment. As a summary, we can say that the larger the connectivity, the more probable it is the consensus, the preferred opinion, as you can get by analyzing this probability. And also the same result is also true for the time. The more connected, the shorter the time to reach consensus in one of the two stages. Now let me go back very quickly to the final part, which is a couple more slides, which is how can these results were for the complex networks in which the agents were not organized. So you have this Erdo-Renyi, where you have probability of connecting, but that probability of connection was independent whether the nodes are biased or unbiased. So we want to answer the following question: Can the bias nodes organize themselves better? Can you reorganize the links such that they reach the goal of reaching the consensus state in the preferred better? What do we mean by better? By better, we mean earlier and with higher probability. And we do that in the following idea. We do rewiring, okay? So we have rewiring, so the total number of links is constant, but we rewire the links in two strategies, which I mentioned very briefly. The strategy one is meet the enemy. So address your links, the bias, address the links to the unbiased. And the second strategy is that the biased nodes get links, a larger density of links among themselves. Let me go that. So that's what we get. So in the first strategy, we move unbiased links, unbiased bias to united to unbiased bias, and then we get this. For instance, this example. This is a random network, and this is the one in which there have been I agree it's not very clear, but here there's a larger density of beings from the biased to the unbiased community. And here we have the second strategy, in which what you do is you keep the same number of links between the bias and the bias community, but you increase the number or you decrease or increase the number in the bias community. For instance, this is an example in which the unbiased community has a larger concentration of nodes. But still, remember, the total number of nodes is the same. We have simply rewired nodes. Which are this is the final slide, which are the consequences? The consequence is the following. If the probability to reach consensus, here, I need to say something. Here, remember, there are two cases. In that case, you can have that the bias community has more nodes among themselves than in the random case, or they have less nodes among themselves than in the random case. We call that a closed community, and we call that an open community. So what we understand is that if we just simply increase the number of bias and bias links, this is less effective than the strategy in you increase the links between the bias and bias. That means that closed communities perform better than open communities. What do you mean by perform better? That the probability to reach consensus in the preferred state is larger than in the other case, and the time to reach consensus, as you can see here, decreases. So if you want to organize yourself, a bias community wants to organize themselves in order to get everybody to reach consensus. In my opinion, what they have to do is to increase the links among themselves rather than increase the links with the other nodes. Okay. So the summary, I will leave that here, and I thank you for attention.
Thank you, Raul. The time is over. Apparently, we have one question in the chat, so please, you can answer directly, and the other questions can also be made by chat, because you must move on. Okay.
Okay.
Thank you very much for your presentation.
Okay. Thank you.
Okay. So next one is going to be. Let me see the program. Let's.
I need to stop sharing. Yeah.
Juan, yes, Juan, please. You can share. Yeah, perfect. Yeah. So your next speaker is going to be Juan Alejandro Valdivia. He's going to talk about the complex traffic in cities under road optimization. He is from the Department of Physics, Universidad de Chile. Juan, please.
I think he's muted.
Oh, your mic is muted.
How about there? Is okay?
Oh, yeah, yes.
Yeah, sorry. Let's start again. Thank you very much for the invitation to give this talk. I'm going to be talking about complex traffic in cities. And this is a work that has been done by a lot of people. For example, Sebastián Carrasco, Jose Rogan, Benjamin Toledo, Pablo Medina, but there's a lot of other people that have contributed to this. The main idea here is that transport in complex networks is becoming a very interesting topic of research. There's a lot of interesting things there. And in particular, city traffic. And city traffic is becoming very exciting because there's a lot of new things that are happening. For example, you have travel optimization software, you have different modes, delivery, scooters, autonomous vehicles, drones, etc. Here you see a picture in which you have that delivery is becoming even more relevant than regular transportation ways, right? Usually we use the car to go from the house to the office. We park the cars there for the whole day, and then we go back at home in the afternoon or in the evening. But now there are more things happening because once we start having like an autonomous vehicle, essentially what's going to happen is that the car is going to take you to your office, and then you're going to send them to taxi, right? To taxi people, because that way you can pay faster. So this is a very interesting topic today, and there's a lot of things and discussions about how to make more livable, sustainable, and healthy cities. So just to start, transport over complex networks is becoming very interesting because it's one of the most popular examples is the internet, in which you are propagating packages along the network. But of course, you can actually discuss, for example, the dissipation of stress of earthquakes, right? You can think of that as a stress propagating along a network of sites. And of course, the more canonical example, I guess, is transport over cities, how cars or people get transported over the cities. Of course, there's a lot more examples than that. So just to start warming up, we can think of the first idea of transport over networks. For example, one example of a very interesting model is the IFISC model, in which you have two urns, and you have a lot of packages that move randomly between these urns. This is also called the dogs and the fleas model. And this was very interesting and very important to understand statistical mechanics, because it gives you an idea how irreversibility appears, right? And what we have done with this model is essentially generated to a number of urns connected in a complex network, and you can do a lot of stuff, because you can do analytical solutions, mean field, and master equations, etc. Right? And the interesting things are the fluctuations. Here we have an example of a very simple network that is connected like this, and the packages are moving randomly between them. And here you have an example of, as a function of time, how the number of packages are in each one of the three nodes or urns, and you see a lot of fluctuations. You see a lot of fluctuations. This is, for example, for blue is the one in the middle, and the red and black are the ones on the extreme of the network. And you see a lot of fluctuations, and this is very interesting. This can be used as a proxy, for example, for a 3-lane highway, and you can think of the cars are moving from one lane to the other, right? You see cars moving from one lane to the other. And what is interesting is in the asymptotic solution, the node or the lane in the middle actually has a lot more cars in general. And actually, if you do it in the highway and start, you can try to observe this, and it's very interesting because you actually can see that. It's a lot of, there's a lot of more cars, because all the cars that are moving from lane to lane, they have to go through the middle one. So essentially this could be called the first Murphy's law of transportation, which is the middle road is always, there's a lot more cars in that middle road. Of course, life is more complicated and you have exit lanes and things like that, or traffic lights. But in general, this is a very interesting concept. So this is our first Murphy's law of transportation in cities or highways. But of course, mobility in cities is a little more interesting because you have traffic lights in particular. And also now we have more modes, or people are using travel optimization software, etc. And people have done a lot of models that use gas or fluids or statistics, right, to analyze these systems. Our interest is trying to model from the microphysics. That means that we're going to have the interaction of how the vehicles interact with the traffic lights and among themselves, right? Here you have a very interesting city, which is Cairo. I don't know if you've been to Cairo, but Cairo is an interesting city because there are very few traffic lights. And somehow the system gets self-organized. You have a lot of cars moving around, but the system gets self-organized. But sometimes because of the fluctuations, you can get to a situation like this, in which the system essentially jams. And the idea of doing the microphysics is to try to model cities, because there's a lot of economic and political and social and even psychological effects on traffic in cities. I mean, I spend, when I go to work, I spend 45 minutes on the road just one way. So this is a very important thing. And as I said, there's a lot of interesting studies to try to analyze the sustainability, habitability, and the health of the city. There's a bunch of papers there. They're going to be at the end also. So just in the warming up, let's start with the simplest possible case. So let's suppose one vehicle. We'll see that even one vehicle in a sequence of traffic lights can be of interest. In this case, we suppose I have one traffic light here and another traffic light here, and you can enter the traffic light at a certain time with a certain velocity. You're going to accelerate to get to the cruising velocity, the maximum velocity. And then you're going to reach to this point in which is a decision point. You're going to look at the traffic light and you're going to see whether it's green or red. If it is green, you will continue at the constant speed. If it is red, you're going to start slowing down. Okay, and whether the traffic line is green or red can be measured, for example, with a periodic function in which you have the sine of omega t plus phi. If it is greater than 0, we call it green. If it's less than 0, we call it red. And of course, as you're braking down, it could happen that the traffic light becomes green again. So in that case, you accelerate again and you try to reach the cruising speed. So we can construct a map that takes the time you you cross the traffic light, the velocity in which you cross the traffic light, and then the next time and velocity at which you cross the next traffic light. And it's very simple to write a model. It's non-linear, of course. And what you see here, you have iterations. You have an initial condition. We can start with 0 initial condition, t equals 0 and velocity equals 0 at the first traffic light. And then you will see that for a certain value of this parameter, which is the cruising time that it will take me to cross this distance between one traffic light and the next at a constant velocity at the maximum velocity over the period of the traffic light. So for a certain parameter, you can see sometimes a period 2 orbit. You cross one traffic light with 0. So essentially you get to 0 velocity and you wait until the traffic light turns green. Or sometimes you pass with an intermediate velocity, okay? 0 intermediate, 0 intermediate. For a different value of the parameters, you can actually get to a more chaotic behavior that doesn't repeat. And here you have a bifurcation diagram for different values of this parameter, and you can see clearly a chaotic bifurcation. And you can see chaos behavior, and you also have periodic. It's very interesting that this happens exactly for range of parameters that are relevant for cities. You can, of course, calculate the Lyapunov exponents, and you can see that the Lyapunov exponents occur when the braking capacity is at least 3 times the accelerating capacity, because this acceleration can be different from this braking capacity. And what is very important is that this velocity, these accelerations are finite. When you have finite acceleration and finite braking capacity, you have this complete bifurcation. If you make an infinity, like in most cellular automata, this chaos regime goes away. So acceleration and braking is very important to have chaotic dynamics, and this is very relevant for city behavior. Of course, you can think of other strategies for traffic, for the traffic lights. For example, you can have a greenway. Sometimes when you have a sequence of traffic lights, you can synchronize the traffic lights so that they're turning green one after the other. So essentially, if you're able to travel at the velocity of the wave, you will cross all the traffic light with the maximum velocity. So essentially, you will optimize your travel time. This is the average velocity normalized by the maximum velocity after averaging over many traffic lights. And you can see this peak at resonance. Of course, if your wave velocity is greater or smaller than the maximum over cruising speed, you will of course have a lower average velocity. And it's very interesting that this looks like a phase transition, what you will have for a phase transition. And it's interesting that this phase transition is very insensitive, for example, to whether we use street with the same length, street with variable length, or even one street from Santiago. But of course, we can actually ask ourselves, should we optimize the wave velocity or should we optimize other things? For example, fuel consumption or even CO2. Here we have the example of fuel consumption for the same bifurcation diagram. And we see that there's a lot more consumption on the right than on the left. And this is because the wave we're traveling faster than the wave. So essentially, once we get to the traffic light, we have to brake and then accelerate again. And that's, you spend fuel, and of course you're consuming a lot of fuel and also doing a lot of pollution. So that's something that we have to think about is what we want to optimize: the travel time, the fuel consumption, or even the CO2 production. And this is going to be very important for autonomous vehicles. Of course, you can think the same thing for a bus, and this is very applicable because in Santiago, for example, we have a lot of buses that have segregated lines in which they don't interact with other vehicles in general. And in this case, the only difference, you will go from traffic light to traffic light is the same, except that in the middle, you will have to, the bus will have to stop at a bus stop and pick up passengers with a certain time tau. And you can see exactly the same idea. And you see a bifurcation diagram for the velocity, you have chaos, etc. And you can compute the Lyapunov exponents. And in this case, the Lyapunov exponents become positive if the braking capacity over the accelerating capacity is at least greater than 4. And as I said, this is very common for buses. And this has been done for city parameters, at least for Santiago. But here we get to our second Murphy's law, which is very interesting. Since there's a stochasticity at the bus stops, you can actually ask yourself, there's an interaction between this nonlinearity, this chaos, and the fluctuations, because you're picking up passengers, so you have to wait. The bus has to wait at the bus stop a stochastic time, a certain random time. And we have done this work in which we realize that actually that it's very difficult to optimize simultaneously the travel time and keeping the schedule because of this interplay between nonlinearity and fluctuations. And this is the second law for transportation in cities. Either you control the travel time, optimize the travel time, or you try to keep the schedule, but it's very difficult to do both. And this actually was mentioned, it was discussed in this Forbes magazine, you know, the ones that with the 500 richest people in the world. They discussed this result, and in many other places. So this was a very popular, very discussed in the news and stuff. They actually interviewed us on the news and things like that. Okay, all of that without car interaction, but now we can include car interaction very simply. We can have, for example, an cellular automata in which we have one car that will move to the next cell if it is empty. For example, this car cannot move in the next iteration because this cell is occupied. And of course, also at the traffic light, the guy will move if it is empty, depending on whether it's green or red. This, of course, is in the limit of accelerating braking capacity going to infinity, so the chaos is not going to be here. We have done a couple of other publications in which we have upgraded this cellular automata, which is very commonly used by transportation people. And we have put finite accelerations in which we have different velocity states, and you can see the chaotic behavior and all of that very clearly, plus the interaction. So you have an extra source of stochasticity. And to this model, we have put a little perturbations, meaning that even there's a 1% probability that even this car will not move to an empty cell if it is empty. And if you put this small perturbation, you know, somebody might be answering the cell, and or something will not be concentrating on the road, or maybe something will cross the road, you know, or a bus will stop. That give you a certain level of perturbation. And in this case, we see the appearance of traffic jams. Even with this simple model, you can see it, because here you have, for example, the traffic light generate this pulse, and you see some people that were dropped at the traffic light by the previous pulse. And of course, this pulse also dropped a number of people, 5 or 6, at the previous traffic light. So what's going on is this pulse is going to pick up these guys, and they will keep going, right? They will keep going, and of course, will drop some people from the tail. And this is essentially the idea of a good traffic jam, in which you are the first at the traffic light, right? And then there's a pulse that is coming from behind, it pick you up, but eventually you will reach the next traffic light, in which now you're going to lose your first position, because you're going to pick up drivers that are stopped at the next traffic light. And essentially your position in the pulse will degrade, and eventually you will get dropped at a traffic light. And this is what you see here. Sometimes you have 5 people drop, sometimes you have 2, sometimes you have 4, etc. So this is the idea of a traffic jam. And it's interesting that you can write the same diagram before. This is alpha, this parameter between the maximum velocity over the velocity of the wave. Here you have the average velocity, and you see when the system, as you increase the perturbation in the system, more fluctuations, you see the same thing that you see in phase transitions, in which your transition gets degraded a little. And we can reach this point for a high level of fluctuations, in which essentially the traffic lights, all they do is separate the traffic in pulses. But beyond that, there's no gain. You cannot do any other traffic control. Here you can do some certain traffic control. They try to have a wave velocity that is similar to the maximum velocity of the driver, or the average velocity of the driver. But here, there's nothing you can do about the control. This is a very interesting emergent state that actually has stochastic resonance and things like that. But of course, lights can be more interesting, because now you can have a complex network of roads and traffic lights. And here you have, for example, one simulation that we have done. This is a pictorial movie of that. You have cars moving, you have a network of roads. We start with a grid for now. I'll talk about what we have done with more complex cities. We're going to have an open city, and this is essentially what we're going to have is cars are moving, right? And we're going to, for example, this car will appear here from in site I. I will want to go to site J, okay, in a random manner. Once they reach, for example, site J, it will complete its journey. So essentially, we generate a new car, and the car will go randomly from point I to point J, and then we have to discuss, for example, the strategy from going from point A to point B, right? One possibility is that this car appears here, that will go from point I to point J, randomly want to go to this position. One way to do that is to have the shortest distance, okay? Or we could have something more like Waze or Google Maps, in which we try to optimize the time of travel, because I know by previous experience what is the average velocity here, what is the average velocity here, what is the average velocity here. So essentially, you can have an estimation of how much it will take me if I take this road or this path or whatever other path. So essentially, I can optimize by distance, or I can optimize by time. And here we're gonna have two further ideas, two further distinctions. One is dynamic. Essentially, every 20 time steps, we go and check the optimization. And for example, the guy got to this point, and now it is better not to use this road, but use this other to optimize time. So essentially, the guy has a dynamic time optimization, very similar to what is done with Waze, by Waze and Google Maps. Or
20 minutes.
20 minutes, thank you. See, almost. A static navigation, or we can have a static navigation, in which we optimize by type, but only once at the beginning. And there's an extra parameter, which is abandonment or desertion time, which will be very interesting. So essentially, you stack a certain amount of time here. You might say, I'm not going to take what Waze is telling me, but actually I'm going to change. I'm going to try this other way. And this is the desertion time. And we can see that actually, after a certain density, here we have optimization by distance, by time dynamic, or by time static. And this is tau, desertion time, and this is rho. And we'll see that for a certain densities, desertion is a very good strategy. So it becomes a very good strategy to desert from Waze or from Google Maps, because after a certain density, desertion can be a very interesting idea. Can optimize the average travel time. And the reason why that works is the following: if your desertion, essentially you never desert because you have very long desertion time, you can see that the roads are occupied either empty, mainly they're empty, or full. Okay, by doing the desertion very often, essentially what you do is you're able to occupy in a better way the roads. You don't completely full or completely empty, so you're occupying the roads in a much better way. So essentially we see that fluctuations are very important. Another idea is to have constant injection rates. In this case, I take a car, put a car here that want to go over here, and once I inject cars every so often, I'm going to see what kind of behavior we have. And here we have injection rate. Here we have density. So essentially I can start with a certain density and an injection rate. And we see that in this case, if you are in the purple, you go down to the attractor, which is this line over here. And if you start in a yellow position, you will go to a fully jammed state. So essentially we have two states, one in which car is flowing, and then another car which is fully jammed. Okay, and this depends, of course, on the type of strategy. And we can see the existence of this phase transition sometimes. Here there are fluctuations because they have fluctuations, and this is very interesting. You can actually construct a model for this, because you have the density. The change in density is the injection rate minus the outflow, and the outflow is about the density over the travel time. And we can write it, the 1 over the travel time, average travel time, we can write it like this, because when t goes to a constant, when rho c goes to 0, or tc goes to infinity, when rho c goes to 1. So essentially we put this in this equation, which is a nonlinear equation, and we can find the equilibrium states, making equal to 0, and we see exactly the same behavior. We have an unstable solution, we have a stable solution. All the purple positions, essentially they tend to the stable solution, and all the ones in the yellow, they go to the fully jammed state. And you can compute the stability conditions and mark these boundaries, of course, without any problem. And if you put fluctuations, you see all of this. And you notice that this is exactly what we see here. Okay, we see exactly these fluctuations, and we see this boundary. And this is very important because it might be used for public policy and urban design in general. We have done this, for example, for Punta Arenas, which is a middle city in the south of Chile, and you see the same behavior, this attractor, and then the jam state over here, depending on which density or injection rate you start. And just to finish, you can think, well, what are the traffic lights are doing? Because people usually use traffic light for control. And we can see, yeah, we have a very interesting behavior depending on the density and the desertion time as a function of the traffic light period over the distance between traffic lights. We have a very interesting behavior, but what is more interesting for us, at least, is here, for example, we have a power law distribution of the time travel over the minimum, or over the shortest path possible between point I and point J, right? So essentially we have a power law distribution, which is very interesting. And in this, on the left, we have, when we have smaller tau, and on the right, we have larger tau. This is a very interesting result, because essentially power law distributions or long tails are telling you that there's a relevant number of drivers that actually taking a lot longer than expected time to travel along the city. So these fluctuations are very important. And the reason for that is essentially you have Brownian motion. You have a lot of different paths in going from A to B that are occupied. And these Brownian motions that actually we believe they're fractal are the reason for that. So I'm done. And the idea here is always moving towards, as I said, into a more livable, sustainable, and healthy city. Thank you very much. And this is the financial support, of course, that we should always say. Thank you very much.
Thank you very much for a very nice talk. I'm spotting here two questions in the chat. Would you like to read by yourself? You want me read it?
Give me a second.
Yeah, in the chat, I see two questions. Maybe there's more.
Yeah. Let me get. I can't see the chat right now. There's
two posters.
Yeah, I cannot see it in my pad. In my maybe.
No, it's sent to everybody.
Yeah. But I probably have to stop sharing if I want to see it.
Yeah, yes, exactly. Yeah.
Chat. Give me a second. Chat here, there. It seems to me that it's similar to the case of Silots, agents that never change opinion. No, that's probably the previous one, right?
The last one. I can read it for you if you prefer.
How does the onset of chaos depends on the density of cars and any other parameter associated to the number of cars traveling around the street? Yes, the cars, what they do, essentially the chaos, what happened is when you have finite acceleration and braking capacities, that chaos bring you an extra fluctuations to the system. And that makes it very interesting because the fluctuations are the one that give you this Brownian motion, or this Brownian motion when you will try to go from point A to point B, right? And essentially give you an extra additional fluctuations into the system, which are what you're trying to understand. The fluctuations are essentially what makes life more complex. For buses, do you consider distribution for the time a bus stay at the top? Yeah, sure. And exactly for the bus, it is exactly the fact that when you stop, you have to spend different amounts of time to pick up passengers. It's different to pick up one passenger to pick up 20 at a bus stop. So essentially, that gives you that stochasticity is exactly what doesn't allow you to do optimization of travel time and to keep the schedule simultaneously. People usually what they do in cities, particularly smaller cities, in which more prediction can be done, is to keep the schedule and not optimize the travel time. But when you are in, I don't know, 9 o'clock in the morning, 8 o'clock in the morning, when you have a lot of people moving in the cities, it would be nice to have a way to optimize your travel time of the buses, but that's not that easy. It's very difficult to do the two things together. Either you keep the schedule or you optimize your travel time.
Okay. Any more questions? A quick one? No? So if you guys have more questions to our speakers to Juan, please just put in the chat. So let's move on. Next speakers, Fátima Velásquez-Rojas. Please, Fátima, could you share the screen with us? Yeah. Mm-hmm.
All right. Okay.
Okay. So Fátima Velásquez is going to talk about the effects of the COVID-19 pandemic in higher education, a particular case from the perspective of complex systems. I'm sorry, I don't see your affiliation here, but you can tell us by yourself. Thank you, Fátima. You have 15 minutes. For Fátima to go, I'll let you know.
Okay. Good morning to everyone. Thanks to the organizers for this opportunity to talk about my current work, titled Effects of the COVID-19 Pandemic in Higher Education, a particular case from the perspective of complex systems. I am Fátima Velásquez-Rojas from La Plata, Argentina. And here, these are my fellows co-authors, Daniela Zacarías, Fabiana Laguna, and Jesus Fajardo. Thank you very much to them. And well, When analyzing a classroom and the dynamics within this classroom, we are facing a system that is made up of individuals who influence each other, emerging dynamics of collective behavior that cannot be explained only by the isolated behavior of the individuals. However, the COVID-19 pandemic abruptly changed the classroom context. For students and for teachers, we had to adapt to a new daily life, incorporating new strategies and tools. In this work, our goal is to analyze the knowledge acquisition process in two different contexts: in face-to-face context before the onset of the pandemic, and the virtual context, that is during the confinement. Also, our goal is to propose improvement to current methods and strategies in the classroom. Okay, but what is the knowledge acquisition? Well, the knowledge acquisition process is a process in which the human being learns and develops her or his intelligence. That is, she or he builds knowledge. It can also be thought a dynamic variable influenced by different factors. In a classroom, these factors can be intrinsics, for example, aptitude, motivation, and previous knowledge on a topic, and extrinsics, that is the interaction of the individual with her or his environments, interaction with teachers, or interaction with peers. Okay, as I said before, the classroom has changed. We came from this situation to this one, something currently widely known for all of us. This research was carried out in the National University of La Plata in Argentina, specifically in the School of Engineering, in the Physics 2 course, during 4 semesters, in 8 sections, during 2 years, 2019 for the face-to-face context, and 2020 with a total number of students equal to 173 students participating in the whole process. Okay, but how to start modeling the KA process? Well, following the ideas proposed by Bordoña and Albano, we can classify the group of students into 3 different sets according to their final achievements. We have high achieving students, HA, average achieving students, AA, and low achieving students, LA. Here, we present the group classification of students according to their final grade in this course and according to their context for the total number of students. And in blue circles, we have the students in face-to-face context, and in the empty orange circles, we have students in the virtual context. In these tables, we can see the separation of the students into different groups and the different contexts. Okay, to model the knowledge acquisition process, we were inspired by our previous work, in which the knowledge acquisition process can be understood as a dynamic variable, that is the sum of big factors. In this case, our hypothesis was that the knowledge acquisition process is the sum of motivation, interaction with teachers, and interaction with peers. And X is the different group of the student, the student group, according to their final achievements. And KF is the final knowledge acquired by an individual I in the course. Okay, at this point, it's very important to know that in our study, we focus on a specific learning related to the classical physics concepts, and this is not the only content of value that is learned in the classroom, and that we simplify the concept of knowledge as a concrete and quantifiable measure. Okay, but how were the data needed for this work collected? Well, we made classroom observations and surveys. The classroom observation, with the classroom observation, we obtained the spatial distributions, the formation of clusters, and the formation of groups of students. And also we made, as I said before, surveys, and with the surveys, we collect the aforementioned factors in 3 different moments: at the beginning, in the middle, and at the end of the semester. With this information, these results were compared with the final grade obtained, and we call to this quantity final knowledge. Okay, the change observed between contexts in this figure, we can see the average final grade for each group of students, in blue the face-to-face context, and in orange the virtual context. And we can see that for HA students, this quantity increased during the virtual context, but for the students in group AA and LA, this performance is decreased. And if our hypothesis is that the final knowledge is the sum of the 3 big factors, let's see how they were modified in each context. We can see in these panels the figure of the average final grade, the motivation, the interaction with teachers, and the interaction with peers for each group of students in the different contexts. And when we calculate the relative change between the quantities, we see that the decreased motivation in all groups for the virtual context, and we can see a change in the way students interact with teachers and other students in the virtual context, I mean. Also, this is more notorious when we saw the network of students between contexts. This is the network of students into face-to-face context, and this one is the network of students in the virtual context. We can see similarities. The similarities is the presence of highly connected clusters, as well as isolated students in both contexts. And we can see difference. The virtual network has nodes that connect 2 different clusters, for example, this one, acting as bridge. And this is a new form of relationship between students, thanks to the new context or the new classroom context, if you want. Okay, the data that we just observed is the raw data that from the surveys, and our goal is to know the different weights that each factor has. For that, we propose 2 different methods: an artificial neural networks and a multiple linear regression method to find these weights. The first method is the artificial neural network. Is a single layer perceptron network. In this one, the dendrites of the neuron is the inputs of the neuron are the data, the training data, motivation, interaction with teacher, and interaction with peers. And then we suppress the activation function, and finally we obtain the output, and the output is each weight, each beta M related to motivation, beta T related to teachers, and beta P related to pairs. Okay, we found generality in the coefficient in both contexts.
5 minutes.
And preponderance of the terms of teacher. In this figure, we can see the final knowledge comparison between the final grade of the students in each context compared with this equation using the coefficients obtained by this method, the artificial neural network. The second method is the multiple linear regression. And in this method, also we found preponderance of the term of teachers, higher weight beta t, and also we found the p-values obtained for these methods indicate that all the regression coefficients are statistically significant. In this figure, again, we can see the comparison between the final grade for each student in the different contexts and the equation of our model using the coefficients obtained by the multiple linear regression. Okay, in summary, we analyzed various quantities that participate in the knowledge acquisition process in the two contexts, in face-to-face and the virtual, for a specific case study. We develop an analytical model based on data consisting of a series of surveys and observations that are contrast with information on academic performance. The shift to virtuality reflects a lack of motivation to learn and a change in the way the students interact with peers and teachers, and the emergent network of contacts built from the interaction between peers reveals different structure in both contexts. Also, we explored two methods to know the weight of the different factors, and in both contexts, the weights are similar. Finally, in our case, the interaction with teachers is of utmost importance in the process of acquiring knowledge. And thank you very much for your attention.
Thank you very much. I'm seeing there's one question in the chat. If you like, you can read directly.
I see. No, I found no. Okay. We do not analyze. No. It's another.
The last one.
The last one. Okay. In my experience, I changed my way to teaching online. At least for me, we're not exactly the same. Do you believe this could be a factor partially explaining your result? Yes, totally. In fact, the evaluation criteria changed, and we observed that in the last semester, the performance is worst. And we think that is for all people have very tired from this situation. The students I don't want to more of that. And yes, the teacher we are convinced that the teacher is very important in this process, but yes, and other factors can be influenced.
Okay, thank you very much. I think you are on time. So any further question, please use the chat for doing that. I thank you all the speakers this morning. So now we are having a coffee break, and we will be back a 11:15. Thank you very much for your participation so far.
Sorry, can I share my screen for my talk?
Oh, yeah, sure.